The ARC-AGI benchmark, Abstraction and Reasoning Corpus, is a program synthesis benchmark whose goal is to assess how AI systems can adapt to novelty at test time. So if we knew the kind of distribution of tasks that are in the test sets and you would, fine-tune an LLM on it, you would solve it. The thing with transduction tasks is that there is no point in latent space that would correspond to your transductive task because by definition there's no induction necessary there. They're exponentially not creative, so you would need exponentially more samples to make them creative. When I solve an ARC task, I have some intuition of what the task might look like in tenth of a second. I see the structures, I see regularities very quickly. And then I realize, oh no, this is not as easy as this. Intuition was happening in large language models is that they have these very intricate, very spurious, highly dimensional, vector functions that can be recombined in some narrow way. I'm a big believer in trying to find, small representations that could explain your outputs. Now, how do you build these spaces? How do you search through them? So my real name is Clement Bonnet. I'll go by Clem.
Okay.
So whatever, Clement, Clem, Bonnet, whatever is easier for you.
Amazing. Clem, welcome to MLST. It's so nice to have you here.
Thank you so much for having me.
So I've just been reading your paper, and Chollet told me yesterday that it's one of his favorite approaches to the ARC challenge.
Oh, is it?
Can you tell the audience about the approach?
The ARC-AGI benchmark, Abstraction and Reasoning Corpus, is a program synthesis benchmark whose goal is to assess how AI systems can adapt to novelty at test time. So it's a very interesting benchmark because pre-trained LLMs perform very poorly on it because it's the tasks that are seen at test time are very different from the training sets. So the whole assumption we've had with this architecture that I'm going to introduce is to have to built in search in the architecture such that you're going to do test time search. And so the way we do it is that we embed programs into a latent space that we train such that it is good to search inside.
So Tufa Labs is a new AI research lab I'm starting in Zurich. It is funded from past ventures involving AI as well, and so we are Swiss version of DeepSeek. So a small group of people, very, very motivated, very hardworking, and we try to do some AI research starting with LLM and O1 style models. What we're looking for now is chief scientists and also research engineers. You can check out positions at tufalabs.ai.
There have been many approaches to the ARC challenge.
Mm-hmm.
And even going back to the days of Dreamcoder, there's Kevin Ellis, and he had this DSL. Well, maybe even before that, we could just search a DSL, which is exponential time. Ellis had a neurally guided search where we train a neural network. And then these days, everyone is embracing this kind of Greenblatt approach where you just make an LLM generate programs. And yours is completely different to all of the other types of test time adaptation. You're embedding the programs in a latent space, and then you're searching that latent space, and you're not actually creating programs. You're generating the solutions directly.
Yes, exactly. So the assumption we had was that we want to do search at test time, and we want to do search in a program space. And to do that efficiently, we try to embed combinatorially hard programs into a continuous latent space that then we can search using any search method that we want. And so by learning the manifold of programs into a single coherent latent space, we allow efficient test time adaptation. So there has been a lot of methods. The top performing methods are using test time training, which is this parameter efficient fine-tuning given a new test input. You search in your parameter space parameters that would better perform on your test input. And so that's a very effective way to do this kind of recombination synthesis at test time. We argue that it's a very inefficient way to do so because the parameter space is huge, and it is not obvious that you can recombine low-level primitives in a compositional way. It is to be seen whether these approaches can solve ARC-AGI, but we believe that by embedding programs into a more coherent and compressed representation, we can do easier, more efficient search.
It might be worth meditating just for a second on why the ARC challenge is so impervious to neural networks. I mean, Chollet wanted it to be that way. Why is that?
Chollet designed it to be robust to memorization. And the way it is robust to memorization is because the input-output tasks are so different from whatever has been seen in a training distribution. It is quite guaranteed that they don't exist anywhere on the internet. It's a private test set that is, kept completely hidden, and therefore it is argued that the task similarity is not high enough for LLMs to kind of generalize zero shots.
I'll just push on that just a tiny bit though. So many of the sentences that we've just spoken in this conversation don't exist on the internet either. So what's the difference between that and an ARC program?
So I believe our discussion can be embedded into a rather small latent space that the LLMs have learned to actually emulate and kind of compose in a way. The ARC-AGI tasks are truly novel, so they're only based on the core human knowledge priors, but they compose these priors in arbitrary ways that I believe are not anywhere on the internet, and that the pre-trained large language models cannot make sense of. Otherwise, you would get zero-shot generalization, which we don't.
This is an interesting thing, just to linger on those. So, are you saying that the reason why neural networks can't learn ARC is simply because there isn't loads of ARC-like data on the internet? It's not, because I think at some point people might have thought there's something intrinsically about the ARC, because it's a discrete program, distribution or whatever, that neural networks can't learn it. But you're saying they can learn it. It's just because there's no data out there.
So if we knew the kind of distribution of tasks that are in the test sets, and you would, fine-tune an LLM on it. If you would fine-tune any neural network architecture on a distribution that includes the test set data, you would solve it. It's machine learning training. But the reason why we can't solve this ARC test task is because the test distribution is quite far away from the training distribution. So it's not able to do extreme generalization and trying to come up with this really novel way of recombining knowledge to perform the task.
MLST is sponsored by CentML, which is the compute platform specifically optimized for AI workloads. They support all of the latest open source language models out of the box, like Llama, for example. You can pay on consumption, essentially, or you can have a model which is always working, or it can be freeze-dried when you're not using it. All of the models that they deploy support the OpenAI API specification out of the box, which means it's just a one-line change in your application to switch over to CentML and start saving money and make your application go faster. This gets to the next interesting bit then. So I guess the reason why, perhaps a few years ago, if you asked me, was it possible in principle at all to learn ARC, I might have said no, because many people, even Kevin Ellis, for example, he loves the idea of generating programs, and that's what Greenblatt did. We feel intuitively that we should generate a program, because then when it runs, on a computer, programs can do this kind of compositionality and various forms of generalization and so on. So intuitively, we think that if we generate the actual answer without going via a program intermediary, then it won't be as good. But is that not the case?
So I'm assuming you're referring to doing transduction versus induction. So going through a compressed program representation, which would be induction based, versus directly trying to predict the answer.
Yeah, maybe we should define induction and transduction, because I think even before you get to transduction, you could train a neural network just to generate the solution directly.
Yes.
And without even using transduction.
That'd be using transduction though. If you predict the output data directly from reading out the inputs.
To me, I define transduction as generating a prediction directly from the data, rather than being a statement about using the solution space. For example, Jonas Hobbiter, his stuff is transduction because, given some input examples, he does some retrieval, and then he fine-tunes the model, and then he does a prediction. So he's building a new model for every single datum that is received. Mm-hmm. But we could build a massive neural network which directly predicts the solution space, which is still an inductive model.
Yeah, so that's where the fine line between induction and transduction, I think, comes in. Also, you have the kernel trick, which turns any induction method into a transduction method. And I believe so. I mean, I don't know if the distinction between induction and transduction is actually matters. I think what matters to me is how much is whether you compress representations. So obviously, when you have an inductive method that comes up with whether it's a Python program or maybe like some kind of latent program, a small representation that is supposed to emulate your output. I would call this an induction method because there is this kind of representation compression bottleneck. And if you're not trying to do that, if you're trying to do some kind of shallow recombination of, just transductive test time training, then I would, put this in the group of transductive methods. And for me, it's all about the compression because compression allows you for more efficient search. In architecture, we build this very compressed representation of programs in which we can effectively search. And I believe when you have some methods about that generate Python programs. I believe these are very similar methods of generating a very compressed low-bit program in Python that can generate an output.
I was going to ask you why a kernel method is not induction.
The goal of linear regression is to come up with this linear function that best explains your data. And so you can, and then once you have this function, you can then use it for inference using a new input-output pair, a new input. When you solve this linear regression of the shape y equal ax, you have a solution of the form xdx minus 1 xdy or something, and so you can actually write the output as a pure function of the training data and your new input, by just multiplying matrices. So I think that's like one representation of the kernel trick. It's just although you have this like very low representation function, which is here a linear function, you can actually rewrite the whole thing as like one computation.
You could, but isn't the kernel matrix is like the training data? It's the inner product of the data, basically,
exactly,
giving you like this positive semi-definite matrix. So is that not the inductive function?
Yes. So essentially, it's like saying y equal fx, and then if you write it out, like kind of unroll whatever computational graph you have, then the whole thing is like a So I think that's where the equivalence between transduction and induction comes in to me. At least how I see it. So that's why I don't think it's a very useful distinction here.
I don't know. I really like the distinction. To me, it's about creating a model from the data rather than reusing an existing model So for example, we could make your model transductive if we fine-tuned the encoder based on some augmentations of the data. But I would argue your system is not inductive now because we're doing some kind of gradient optimization through the model, but we're not changing the model. Therefore, it's inductive.
Yeah, we're not changing the model. That's the whole thing. Although I do think that so our latent program network LPN search is actually I think fits in a spectrum of test time training methods. So if you see the latent space as an input conditioned parameter space in a way, we are training this space. We are like searching through this space. Using zero order or first order optimization methods to find a better explanation for your data, and it's quite similar to searching through your parameter space, doing parameter fine tuning at test time. So I do think they fit in the same spectrum. I'm curious to explore methods where this adaptation at test time would be as efficient as possible. If we want to create systems that adapt online very efficiently, and so I really like test time training. I do think that. They're not. It's probably a very suboptimal method, searching in this vast parameter space.
So, can you talk me through the architecture?
So, as I said, we want to embed programs into a latent space. So, to do so, we have first an encoder that takes input-output pairs independently, and then embeds them into a program similar to a VAE architecture, actually, a variational autoencoder. But if you think about it, an input-output actually can be explained by an infinity of programs. Right, or varying description length or complexity. So we would want to find a minimum description length program. But so because you can explain input-output pair with an infinite amount of programs, we use a variational framework. So we encode these programs into a distribution actually of latent programs. So we embed these input-output pairs into a distribution of programs. And then we have this like search component in the middle, which I'm going to explain right after. And then once which is all about refining this latent to be a bit better. And then once you have a better latent, you try decode it with your decoder. And so your decoder is actually going to take a new input is going to take this latent program and then generate an output for it. So it's literally applying a program. So I'm saying programs here, but I mean actually latent vectors. We all in a geometric space here. And so the true novelty, I think, of this architecture is actually this middle stage here. And how it works that we expect the encoder to actually output a first guess of what the program looks like, a bit as a human intuition when solving an ARC task of, oh, I do believe there's something about shapes here and like we should like move them around. So that, it's like first guess. And then we use optimization methods to refine this latent to find actually a different point in your latent space, in your latent program space, that would better explain your data. So you have this kind of inner loop with that uses the decoder and the input-output pair, so your specification, to find a better latent in your latent space that would actually, for each of the input-output pairs, would generate the right output. And once you found this, a further away point in latent space that better explains these input-output pairs, you're rather confident that you can apply it to your new test inputs. So I think that's where the induction part here comes in, because we're really trying to find this, small representation, small latent program that explains your whole task.
So ARC, let's say it typically comes with about 3 and when we say specification, we just mean like you get a few input example pairs, and you can place all of them through the encoder, and the encoder will give you 3 different points in the latent space. You average those together, and then you perform some gradient steps to improve the latent to a point where you get a good solution for all of the 3 examples, something like that.
Yes, it's exactly that. So we have so we must find a way to recombine these different latent distributions for these different input-output pairs. Ideally, each input-output pair should actually, through the encoder, should generate a roughly similar latent distribution, because they actually correspond to the same inherent task. And so the vanilla way of doing so is to actually compute a mean in latent space and then use that as a starting point for your search. I do believe there are better ways to do so. We could see the whole aggregation as a mixture of distributions, and probably like, I don't know, maybe sample with a small temperature or something. I do believe there are better ways to aggregate these kind of distributions. A first proof of concept we've done was this mean aggregation, which ends up working pretty well. And so the nice thing about this architecture is that it's trained end to end using a variational VAE loss, so the elbow loss. So this means it is decomposed into 2 terms: the reconstruction loss. So given a latent program that is refined, try to reproduce your input-output pair given all the other input-output pairs in your specification. So you have a reconstruction loss, and then you have a prior loss. Make sure your latent space looks roughly Gaussian. So this is the classic prior loss from the VAE, and it actually encourages the latent space to be very structured. We did try without the VAE framework, so the pure autoencoding framework, so no prior on what the latent space should look like, and we end up with very unstructured, spiky spaces where most programs tend to be as far away as possible from each other, making search impossible and making the whole latent space rather useless. So I think the variational aspect of it is very important, trying to keep a Gaussian compressed representation of your program space.
Yeah, we should double click on that a little bit. So we want to have a well-formed space that doesn't degenerate and doesn't memorize solutions. And I think you also use the KL divergence. Just reading from your paper a little bit here. So you said that you want to prevent encoding the output directly in the latent space. So you encode an input-output pair to the latent space, but train this representation to decode the output of a different input-output pair to prevent memorization. So that was one of the tricks that you used.
Yeah, so actually it's not really a trick. It's so with most of these latent space ideas, usually when they don't perform them on program statistic benchmarks like ARC, there's usually this problem of you want to learn a compressed representation of whatever your input-output space is, and then try to decode it. But the obvious thing is that you may actually end up just compressing your output in your space. You would kind of leak your output in that space, and so it's easier to reconstruct. It would be a shortcut that ML training would lead, and it would be very useless because you wouldn't learn anything input that connects the input to the output. You would just learn to map the output to a latent space. So the way we deal with this is just we consider during training we use a very similar setup as we would have during tests, which is we have access to n input-output pairs, and we want to predict an n+1th output. So actually during training, if we assume n input-output pairs, for each input-output pair, we are going to embed into the latent space the n-1 other pairs to predict that pair. And we kind of do that for all the pairs in parallel.
Very cool. Now the other great trick you used is you actually do like gradient steps, so search steps during the training process, because it actually makes the final kind of latent space more amenable to search at inference time. Was that something that you thought to do intuitively, or you did it to help it because it wasn't working?
Yeah, so we've always wanted to train using search, and the reason why we want that is that if you think about it, during training, your encoder will, well, even at the end of training, your encoder is not perfect. The whole assumption is that it provides a best guess of what the task is. And so if you're not allowed to kind of refine this guess, well, the decoder can be as good as what the guess from the encoder is. So you end up with a latent space. Well, you would end up with a latent space that cannot really encode many programs. It would just encode kind of the regression to the encoder's best guess distribution. So what we end up doing is that we actually activate this search method during training. It brings significant overheads at training time. So we actually propose some kind of pre-training without it, and then kind of fine-tuning with it. But it doesn't matter. The whole point is that by switching it on during training, using some kind of random local search or gradient ascent first-order optimization search, we train the latent space to be good at being searched. So the best guess ends up being actually quite bad, but very close to a very good guess. It's the whole point behind these meta-learning methods like MAML and so on.
Qualitatively, tell me about the latent space. So, you've looked at it. Do you find that different directions correspond to different types of ARC problems or whatever? What do you see?
So we haven't analyzed the latent space that much by comparing different ARC tasks yet. I think it's a very interesting thing to do. I think in the paper we do bring up a plot of kind of a TSA interpretation of the different programs that are learned, and so during training we definitely see this kind of blob of like all the input-output pairs that are not really well understood, neither by the decoder or by the encoder. End up being in this kind of bag of unlearned programs, and programs that start being learned start to cluster and occupy the space. So we kind of scaled this architecture for ARC very very recently. We got some non-zero yet non-SOTA results, and I think it's interesting because although we don't get very very high performance, we do get it without any priors, so without using any pre-trained LLMs, without looking at the evaluation set or whatever, by just training on the 400 train test distributions. So getting something like 10% on the evaluation set, which is in itself actually a harder distribution of task, was quite impressive, I think, from the first initial scaling curves we've had.
Can you explain that bit in a bit more detail? So you've got an encoder and a decoder and their transformer models, and you've got the re-arc tasks from Michael Hoddle. And what kind of transformers were they, and what kind of training did you do?
Yeah, so the LPN architecture assumes this encoder and decoder modules, and to train this architecture on ARC, we really used vanilla transformers from scratch to encode the input-output grids. So really, you could use any generative model, any sequence model. We decide to use self-attention transformers that kind of flatten the input-output grids into sequences of 900 values, because these are 30 by 30 grids. We use some kind of roughly smart 2D positional encoding to make sense of spatial structure, but that's roughly it. And then we train rather small transformers. I think they're about 20 million parameter each, roughly 40 million in total, on encoding and then generating autoregressively these input-output pairs. We didn't tune the architecture that much, we had to do something, around the positional encoding to make sense. But otherwise, it's a very vanilla transformer pre-layer norm architecture. We really focused on trying to get a good latent space of programs and how to efficiently search it during training and at test time. And we experimented with the transformer architectures at first, and we're like, okay, we're good to go. Let's just focus on what we think is interesting.
This blows my mind because most people that use transformers fine tune them. They take ones that have been trained on internet data and they fine tune them. And I guess like the intuition for that is we're told it's very difficult to train transformers and they only start doing good things when you train them with loads of data for a very long time. So you started from scratch. I think you said you didn't even train it to convergence, just with like Michael Hoddle's ReARC dataset, so hardly anything, and it still worked quite well.
Yeah, so the whole point during for our training was to learn to embed these 400 trained tasks in your latent space. And if we do so, in a rather structured way, then we hope that by interpolating this latent space, during search at test time, for instance, giving a new input-output pair, give a new task, then you would find programs that are not seen during training, but that, represent kind of interpolation, probably superposition of programs seen during training. Training a transformer on single input-output pairs from a single program is a very bad idea. There's not enough data for the transformer to make sense of relative positions and so on. So we use Michael Hoddle's very useful library of ReARC transformations. So the data Michael Hoddle created is just a distribution for each of the 400 tasks. It's a distribution of input-output pairs following that program. So the program is constant. So there is not a lot more information that we extract. Really, the program is constant. It's just the input distribution is now a rather broad distribution instead of being a single input. And so this allows training transformers to make sense of 2D grids in a way that they would not when they're initialized from scratch. We do show some kind of some training curves on ReARC. We actually didn't have enough compute to train till convergence, but we showed kind of some increase of accuracy on the train sets. We do believe there are some bottlenecks in the architecture that make learning very slow or not, that wouldn't converge to 100%. So yeah, we're figuring this out.
And in this ReARC dataset, so 400 tasks blown up with this dataset generation that Michael does, how many how many program examples do you have?
It's in order of 100 million data points.
It's a lot then.
It's quite a lot, yes. Okay. We do sample a lot these programs. Yeah. I think transformers are really bad to make sense of random sequences of pixels, like when they train from scratch, of course.
Yeah.
So that's why we really have to do this intense training of, making sense of these input-output grids, which is something, a bit silly, but we believe ARC-AGI is actually, as François said, a developer-aware generalization benchmark. And so we really wanted to have no priors from anywhere on the internet, so to not use any pre-trained LLMs, and really to train architecture on the very little data that is that matters to the task.
Isn't the ReARC dataset generator a prior though, like a pretty big? I mean, to me that would invalidate the developer-aware generalization.
The priors contained in ReARC are all about when you actually have an input-output pair with 2 objects. Well, you could have the same with like 3 objects. So you have the prior of counting, for instance. I do believe in the task you also have these other priors of objectiveness and so on. For us, it's very much the priors used contained in ReARC are very much to teach transformers how to make sense of 2D grids, because the 2D grid space is huge. It's 10 power 900 for each grid. And obviously, most of these 10 power 900 grids don't make any sense. They kind of white noise. So we use this distribution to kind of feed in some of the human priors into architecture, which I believe is in line with the developer-aware generalization assumption.
Yeah, we can debate that. How did it generalize to different grid sizes? I mean, of course, you're using transformers, so you turn it into a sequence, right? But did you notice any weird overfitting on sequence size?
No. The way we deal with the shapes is very naively. We actually predict the shape first. So let's say you have a 10 by 10, 10 by 11 grids. we actually predict, it's going to be 10 rows, 11 columns. And then we have the 900 tokens corresponding to the padded 30 by 30 grids, most of which is actually padded and ignored by the transformer. But so we end up with actually sequences of 902, tokens values per grid.
Yeah.
That's how we, predict shapes. I think a lot of things to say about how to optimize this. We don't think it's an optimal way to do so, but it's it's probably enough for ARC, or enough given that you have a lot of data to train on.
Yeah, I suppose this might be an example of why generating an explicit Python program might be better, because it could generalize to different grid sizes.
Definitely. So Python programs, grounded programs, executed by an interpreter, would make sense of all these priors that are not contained into a randomly initialized transformer. So yeah, I do believe real programs are also a very smart way to do induction, to compress your rotations. One of the problems, of course, with program search is the combinatorial expansion, combinatorial explosion of the search through your program space. And so we really try to compress that by learning the manifold of programs that we hope would be easier to search. But obviously it comes with some caveats, and potentially you can't represent all programs into this latent space. So yeah, I think there's interesting ways to maybe try to think about combining both ideas. But there are pros and cons for like program search and latent program search, I believe.
Yeah, I'm just thinking back to when I first interviewed Chollet years ago. He always said there are type 1 and type 2 problems, and type 2 problems are not interpolative. But we're taking it as granted that this is actually interpolative after all. So we have this latent space, and it's got all of these modes in, and we do this test time computation. And the more test time computation we do, the better the results. And at the moment, if I understand, you're using like a first order kind of like gradient search method. So first of all, talk me through that. So you do more search at inference time, you get better results.
Yes, but just before that, I do believe type 2 problems would not work with our method. So I do believe one of the big limitations of learning a continuous latent space is actually you can't fit arbitrarily complex combinatorial programs in it. I think you can do some things like superposition of programs, but I don't think you can do composition of programs. Which is obviously what we're trying to look into as a follow-up work. I do believe that you would not be able to get composition by searching through this latent space. I think you can get some composition, like maybe just a couple steps of composition, but at the end of the day, it's a fixed continuous latent space, so it's unclear whether you can really compose objects with it.
Right.
Now going back to the search.
Well, just before we get there, this
yes.
is like you've really touched on an interesting point. So this gets to the core of it, right? So people like Gary Marcus and what Chollet was intuiting is the lack of compositionality. So you're saying, okay, there is no compositionality in the latent space, but we could actually come up with some kind of a compositional inference time method that gives us compositionality. So if you think about it, we could have multiple search threads through the latent space, and we could have some system 2 program that like composes the things together, and we could get the compositionality but still use your method. Is that kind of what you're saying?
I think that's a promising approach, a promising way to think about it. I do believe that single threads search in this single latent space would never bring you composition. But something like having, multiple threads, as you said, or some kind of like multiple things happening at the same time being kind of synthesized thereafter could be a way to get composition. So I think what we wanted to do is kind of a POC of how to try fit as many programs as we can in this latent space. I think now it opens up, lots of possibilities to extend this further.
Then we have the matter of, if we were generating like symbolic programs, it feels like we could compose them together. Like, for example, we could learn some iterative, like, steps of functions that just get composed together. Whereas in this case, we have solution predictions directly. So let's say right now I've got 3 solutions that I've found that represent some kind of, 3 different types of transformation that need to be composed together. So now we need to have a function that can somehow take those 3 solutions and combine them together.
Yeah, so I do think you would need some kind of an unrolled computational graph. So I don't think you can easily look at these three solutions and kind of synthesize them in one shot. Intuitively, it would be equivalent to actually having only one like better thread or something. So if you want to try to explore different regions of your space and then try to combine them, maybe you would need to kind of do multiple forwards or something. So maybe like one thread gives you some kind of primitive program, and then you apply the second thread on the output of the first primitive, and so on. This way you would get like a recursive unrolled like computational graph. I mean, yeah, I think it's up to it's a research question how to think about these things.
Yeah, or how to train that would be difficult. But even maybe like you could have an intermediate stage where the decoder could take in multiple inputs, and it could learn to compose them together to a fixed depth, because like language, it's not actually that compositional, right? Like we only use a depth. Some languages don't use depth, but English, we have a depth of up to like 3 or 4 or 5 or something. So you might find that most of the the colloquial ARC problems that we'd ever want to solve would have a fixed depth, and we could somehow encode that in a neural network.
Yes, and actually the ARC solutions using brute force program search have a depth varying from 1 to usually something like 12, 15, and sometimes up to like 50. But like for most tasks, actually, you can solve them using a rather small length. So yeah, very
exciting. And we're pragmatic people. Like I love the theoretical arguments about compositionality and symbolic AI and so on. But in the real world, we don't actually need to have this infinite composition.
Going back to the search methods.
Yeah.
So our whole assumption is that there exists a different program, latent program in your latent space that is better than your first guess. So the question is, how do you find that program? And so it's just a matter of, it's a question of search now. And we actually tried two things. We tried some kind of zero order random search, local search around your first program. And then we actually realized that the latent space itself that was learned during training ended up being very smooth. And so when I say smooth, it's smooth with respect to the decoder likelihood of decoding the right output. So you want to kind of maximize the likelihood of decoding your right output. So this latent space ended up being very smooth, which allowed us to use first order methods. But I do believe that potentially with different tasks, or if we train for longer, you could have some more discrepancy and kind of local optima in this space, which would maybe bring to the table methods like evolutionary strategies, zero order methods or maybe a combination of the two. But for our use case, it worked very well to use gradient descent. I don't think it's the best method, but yeah.
Okay, so at the moment it's quite smooth. It's quite amenable to simple like gradient ascent methods or whatever. That's all cool. What about its resilience to, I don't know whether you tried putting noisy inputs in, or another thing is like you could almost undertrain the architecture, but do more searching. Like is there a relationship that you've explored there?
So we haven't tried putting noise and shooting ourselves in the foot. Maybe we should, but we have tried scaling architecture size though. So obviously if your transformers are too small, well, for sure they can't decode your output very well. So yeah, there's kind of a trade-off, or at least it goes, architecture size and like latent space size go like hand in hand. So yeah, we did see that when the architecture size is too small, well, you can't even make sense of the sequences very well, and hence you can't like decode your program very well, no matter how big your search space is. So we need to actually, when we train this architecture, there's not a lot of like tuning to do, but we need to make sure that the decoder's capacity is high enough such that and your latent space is big enough such that there exists a point in latent space that corresponds to the right program. And given that point, you have enough capacity to execute that program, which is not the case when you use Python programs. You're sure your interpreter will execute it well. You just need to like find it. So yeah, you have this like second constraint here of like making sure the decoder can learn that program. And we actually have preliminary results showing that they were not in the paper actually, but showing that it's not obvious that the decoder can actually learn like all the tasks. There's also a paper mentioning this issue. So and it boils down to what priors you feed into your architecture in terms of like 2D spatial representations and so on. So yeah, it's a trade-off how much time you want to spend on like optimizing, your architecture to solve a specific benchmark versus how much you want to like improve the the method itself, i.e. like the searching latent programs.
Very cool. So Ellis and Wending, they just released this paper to, sort of like comparing induction and transduction, and they had this ensemble approach where they kind of did both at the same time. They've got this beautiful Venn diagram that shows that, sometimes induction with Python programs works really well, sometimes solution space works really well. Have you kind of like done analysis on what types of ARC, tasks work well and don't work well on your system?
Yes, so we don't have very strong analysis on this, but from what we've seen, most of the bag of programs that are not learned often correspond to transductive tasks, transduction tasks. So I think it's very much aligned with their paper. It was a great paper highlighting this. We actually, when it came out, maybe a week or so before the ARC prize deadline, we thought, oh, it's actually what's happening. We struggle learning this transductive task, and yeah, I think there are obvious ways to kind of use this ensembling technique also for architecture or for other architectures. The thing with transduction task is that there is no point in latent space that would correspond to your transductive task, because by definition there's no like induction necessary there. So it's all in the decoder, and I think there are ways to like help the decoder with that essentially. We just try to remain as benchmark agnostic as possible, trying to not overfit to ARC. But I think there are obvious ways to improve.
Is there a story that you're kind of like, you're not a symbolist?
I've always been a connectionist, and I'm kind of new to like trying to improve connectionist architectures to tackle this like maybe 1%, 10% task that people are really into these days of like reasoning, search. I do believe in a future where maybe probably most of your task can be tackled by kind of one-shot deep learning based architectures like LLMs, but actually some of the hard like last mile, hard like 1% task need something a bit different. So yeah, I'm a strong believer in like deep learning and program synthesis kind of being merged to achieve that like last percent of task.
So you're not amenable to this school of thought that these things are just smarter than us. We just let it do the thing.
I think we can't comprehend arbitrarily combinatorial sequences of symbols, and so that's where connectionism like comes in as very useful, because we try to learn manifolds of complexities. I think it can bring you very far, and it can only bring you so far, and that's what I mean by I think that deep learning architectures can solve something like 90%, 99% of the task, but there will all be some tasks that are probably like discrete inherently, or tasks that require like long horizon planning and reasoning, things that we're trying to tackle with LLMs and other deep learning architectures nowadays, but very recently actually. And I do believe that other architectures could do this much more efficiently. I think it's connected to creativity as well. I believe deep learning models are not highly creative. I will not say they're not creative, because as we can see with going back to ARC again, the like solutions like Ryan Greenblatt's solution of sampling a lot of programs, and you kind of see this logarithmic scaling curves as you sample more and more programs. Well, this means that there is if you like plot the distribution of possible programs sampled by an LLM doing outputting codes, well, you have some non-zero mass on like with long tails on very like creative and good solutions, right? And you only get these solutions if you sample like 1 million times. So this way, I think I can't say that they're not creative, because, well, if you sample high enough, like they will create these things. But I do believe that they're exponentially not creative. So like you would need exponentially more samples to make them creative. I think that's why symbols can actually maybe help by doing symbolic program synthesis, or what we call programs, maybe just sequence of symbols. We could fight this creativity issue by very easily going into a combinatorial space that is completely novel, and that you can't really keep track of, you can't amortize, and fighting things like going into things like computational irreducibility. So yeah, I do think a program synthesis could help, and symbols could help deep learning architectures to become more creative. Don't know if that makes sense.
No, it does. I'm very interested in creativity. I must admit, I think I might have actually changed my position on it, because I took a very almost human chauvinist approach to creativity. That there's a creativity gap in LLMs, that we have access to a sort of source of creativity that LLMs don't. And so many people I've interviewed in Europe are just telling me the opposite. In fact, Sabaro Kambahati said the opposite in June at ICML. He said no, these things are very creative, and part of that is because creativity isn't just about novelty; it's also about interestingness. It's about things that we find interesting given our cultural biases and interests and so on. So they seem to capture a lot of that. And then, okay, you can say, well, we can greenblatt it. And yeah, we have to sample 30,000 times to get something interesting. But is that so different to us? Like, we're this huge collective intelligence, and we're all coming up with ideas, and most of them are rubbish. And every now and then we have this flash of inspiration. And perhaps we're embedded and situated. We have access to all of this entropy and whatnot. But is it really so different?
Yeah, I think there's something to say about collective intelligence. I haven't thought that much about collective intelligence in general, so not sure I can comment very well on that. But if you focus for a second on individual intelligence, it seems obvious that you don't sample a million programs in your mind when trying to solve an ARC task or when trying to come up with something creative. There is, some kind of synthesis that is much more efficient happening in your brain. And I think I'm interested in trying to get closer to this kind of synthesis. Now, I do believe there's something, very interesting things to say about collective intelligence, which brings much more, entropy and a lot more of the sampling that we talked about. So maybe both schools, could come up with interesting breakthrough.
When you solve an ARC challenge, are you being creative?
Well, the way I think about it, when I try to solve an ARC task, So again, I have some intuition of what the task, might look like in tenth of a second. I see the structures, I see regularities very quickly, and then I realize, oh no, this is not as easy as this. And then I try to, I propose a few hypotheses, maybe 2, 3, 4, and I refine them, and then the fifth is actually correct. Check it matches all specification, and I just apply it, and I get it. So this is maybe on half of the task. On the other half, it takes me a bit more time, but that's the idea. I do believe we have this kind of few introspection, few hypotheses that we propose, and these hypotheses seem to be quite creative in a way that they could be very different from each other, and yeah, I feel like they would recombine priors in a way that is quite combinatorial and compositional. I need to stay humble in how I solve the task because many of them I actually struggle with. But I think it's this idea of coming up with a few hypotheses, testing them, but not coming up with a million hypotheses.
Yeah.
So it's how do you cut down this search space in an efficient way. There's probably much more than that in human cognition. I think getting this would be a good approximation, at least.
If we scaled your solution up ridiculously, right? So, much more training data, much bigger model and so on, and we trained it for longer, what do you think would happen?
So I think it could scale quite a bit, especially if we scale the latent space. I do believe it would be very... So I think one limitation is how much you can actually search in that space. I would expect this space to be actually not that linear, not that interpolative, not that smooth. And so if you end up scaling a task and problems, I would end up this space to actually be harder to search. So it's going to be about how much search you can do during training. You would need to scale this up probably, keeping everything the same in this architecture. And so it would actually be quite costly, I think, to scale both the kind of encoder, decoder, and the latent space as well, and the search in this latent space. So I think there are better ways we could iterate on this idea. I do believe coming up with a small representation of whatever task, whatever query you have, can be a very useful way to do synthesis, to adapt, to deal with epistemic uncertainty as well. I do not believe we can estimate epistemic uncertainty currently, but I think searching through this space could help resolve some uncertainty.
That's very insightful. So you're saying when we actually scale this up, the latent space might become less interpolative. Could we do meta optimization, or could we have a different type of latent space, or I'm just sort of spitballing here, but some kind of topological space, or some kind of graph representation, or what else could we do?
I think it's not just about scaling the latent dimension of your space, which has been the case with large language models. I think what's from my intuition, what's happening in large language models is that they have these very intricate, very spurious, highly dimensional, vector functions that can be recombined in some narrow way, and it's very useful, but it's very it's very local. Like you're trying to find like the abstraction locally that like is a little bit better, and I think it doesn't give you all these things around composition and auto distribution generalization. So yeah, I'm a big believer in like trying to find small representations that could explain your outputs. So for like natural language would be a query and then the answer to a query. Now how do you build these spaces? How do you search through them? I think these are all open questions. I've seen lots of interest in the direction lately, so it's very exciting.
Yeah, amazing. Well, congratulations on the work and your recognition from Chollet. Completely blank slate, unlike any of the other approaches. Very interesting indeed. So yeah, keep up the good work, and thank you for coming on.
Thank you so much, Tim. Thank you for having me.